So I've spoken several times during the course of this chapter about molecules having to collide to have a reaction take place. So that's called collision theory or the collision model, which simply says that molecules have to collide for a reaction to occur. And in order for that reaction or that collision to actually be successful, you have to have enough energy in the collision. That is, there has to be enough kinetic energy, and the molecules have to have the right orientation. That is, there may only be one part of a molecule that is available to have a bonding event with another molecule, so they have to be in the right orientation. If you're a biologist, you may be familiar with enzymes, which have active sites, which are a small part of these large proteins in which a reaction can be facilitated or catalyzed, and that is in the active sites of these enzymes. Okay, so in collision model, you have to have enough energy and you have to have the right orientation for a collision to be successful. And so this is an energy progress or reaction progress diagram, which reflects the energy of the reactants and products, what's going on, what the energy barrier, whether a reaction is endothermic or exothermic. So let's just take a look at what we've got here. Now on the y-axis, we've got energy, and the higher you go on the y-axis, the higher the energy. This is higher, and this is lower. I think maybe I'm going too far with over-explaining this, but in any case, the reactants are at this energy level in this reaction progress diagram, and the products are at a lower energy level. And the difference between reactant energy and product energy is what we call the change in enthalpy, or delta H. And you may remember from Chem 1, we calculate delta H as the enthalpy of the products minus the enthalpy of the reactants. Okay, so if we do that in this particular case, you're going to see that we have a lower product enthalpy or energy than we do reactant. This is a higher energy level. And so if we're taking a lower number, we're subtracting a higher number, we're going to get a negative number. And so that's going to give us a negative delta H. That means that energy is being released. Okay, we'll just call it heat is being released in this reaction. And you know what we've got here. When energy is being released, we've got ourselves an exothermic reaction, and our delta H is a negative value. Now, the other energy story in this reaction is that there is a barrier to the reaction actually taking place. So we've got the reactants over here at this energy level, but in order for them to reach that level of energy where the reaction could take place, otherwise reactants would just be converting to products all the time. They would be tremendously unstable, and you could never have a reactant lasting for any length of time. So you have this energy barrier, and you can think of this, I sometimes I've taken some long trips. I used to ride a motorcycle, and I was sitting in Denver and I wanted to go to Dallas, and just think of this as a mountain that's in the way. And in order to get to Dallas, I actually had to expend a tremendous amount of energy to get to the top of the mountain. Now, we call the top of the mountain the transition state. And as the transition state, this is where reactants are transitioning to products. So we call that the transition state. And this barrier between the reactant energy and the transition state, this is what we call the activation energy, and we'll just call that E of A. So that stands for activation energy. Okay? And that is always endothermic. You always have to put energy in to overcome that energy barrier to get to the transition state. And this is the activation energy specifically for the reaction in the forward direction. Okay, reactions have directionality. They can go forwards and sometimes they can go backwards. All right, we're going to talk about that as well. Okay, so we have this energy diagram is describing an exothermic reaction. The features are the delta H, which is simply the difference between product and reactant energy. You should know that. And in the diagram, this is describing what we call the activation energy. That isn't written very well, but you can read it right here. And we simply denote it as E sub A. The higher the activation energy, the slower the reaction. Just like my trip from Denver to Dallas, if the mountain were any higher, if it went even higher, it's going to take more energy to get to that higher transition state. So the bigger the activation energy, the larger that value, the slower the reaction. And we can simply depict that by this diagram. Okay, I cleaned up my diagram because it was getting a little bit messy, and I've got some more that's going to go into it. So the top of the energy barrier is called the activated complex or the transition state. Activated complex and transition state are synonymous. It's just reactants are being converted to products, and the rest is sort of a downhill slide. All right, so activation energy, that is the difference between reactants and the transition state for the forward reaction. And then we could also describe the activation energy for the reverse direction. In this case, we're actually treating the products as reactants. So here's my products, and we're just going to imagine this reaction running in the opposite direction. So we're going from products to reactants. Well, that's representing an endothermic process. And the activation energy, since the products are now being treated as reactants, is from the product energy all the way back to that same transition state. So if I knew the activation energy for the forward reaction and I knew the delta H, the activation energy for the reverse reaction of an exothermic reaction would simply be the sum of the delta H and the activation energy for the forward reaction. Now that's only going to work if the reaction progress diagram is for a forward reaction and you're computing the activation energy for the reverse reaction. I want you to remember that activation energy is always endothermic. Okay, so it's always going to be endothermic, which means it always has a positive delta H. If you compute an activation energy for any reaction and it's negative, you're wrong. It's always positive. All right, let's take a look at the Arrhenius equation. Well, very simply, let's just throw it up there. Here it is. Now, the Arrhenius equation has a number of features. Let's say I take a rate law for a zero order reaction. Now, this is K. This is the rate constant. And I think that you can see that if this is the rate constant and this is the rate law for a reaction, and it is for a zero reaction, that if I find some way to increase K, that's going to increase the rate. If I have a way to decrease the rate constant K, it's a direct relationship. That's going to decrease the rate of the reaction. They are directly related to each other. So you know how that works. If you change one variable in one direction, you change the other variable in the same direction. All right, so here's the Arrhenius equation, which describes the effect of activation energy and temperature on the rate constant K. This is called the frequency factor A, and the frequency factor just describes the number of collisions that are successful in a reaction. Now, this is the exponential factor. Okay, so the exponential factor is this minus E of A over RT, which is the exponent for E. This entire thing is the exponent of the E, which is the antilog to the natural log. So what would be the effect of K if I did something like raise or had a reaction with a higher activation energy? Well, you know what happens. If the activation energy is higher, the reaction slows down. Why does it slow down? Because it causes K to be reduced. And if K is reduced, the rate is reduced. The rate slows down. Okay? Now, let's take a look at temperature. If I raise the temperature of my reaction, I'm going to change K. K is going to be different. What that's going to do is it's going to give me a larger denominator, which makes this negative exponent smaller. And so what's going to happen is your K value will go up. Well, if K goes up, the rate goes up. So that's the effect of activation energy and temperature on the rate constant. So if you're asked a question about why temperature changes, if you change the temperature of your reaction, why it changes the rate of the reaction, it's because it changes the rate constant. If temperature, on the other hand, let's say we go in the other direction, we make temperature a lower temperature, what's going to happen is exactly the opposite. K value is going to go down. And if K goes down, the rate goes down. So that's how temperature and activation energy will affect the rate of the reaction. They affect it by changing the rate constant. And that's going to be important in the next section. So, an increase in the activation energy, that's E of A, results in a decrease in K. That slows down the reaction. So that's why increasing the activation energy slows down the reaction. It lowers K, changes the rate constant. An increase in temperature results in an increase in the rate constant, speeding up the reaction. And exactly the opposite if you lower the temperature. Okay, so changing K changes the rate. That's what you want to remember. Okay, changing the rate constant changes the rate of the reaction. So if I want to get rid of the antilog, I simply take the natural log of both sides of this reaction. That's going to give me this version of the Arrhenius equation. And I'm betting you can figure out what's coming next. This is going, the natural log of K will be Y. My slope will be negative E of A over R. So that's going to be my slope. This is going to be my X value on the X-axis, and this will be my Y-intercept. And so I can graph that, and if I were to run a little graph here, I've got the natural log of K here. I wind up with a straight line with a negative slope. Here's the y-intercept B, which is going to be the natural log of the frequency factor, and I have minus E of A over R, and that's my slope. Okay, and then down here on the x-axis, I have 1 over the temperature, and this is the Kelvin temperature. You always have to be in kelvins for any of those reactions. So that is the graphable natural log of the Arrhenius equation, and we're going to play around with that right now. You now know that changing the activation energy or changing the temperature will affect the value of K, and we can use the Arrhenius equation, for instance, to solve for the activation energy, to solve for K, to solve for the temperature at which a particular reaction is going. So it's a very useful equation. But we're going to go ahead and we're going to do a derivation for you at two different temperatures. The first thing I'm going to do is I'm going to take the natural log of K and the natural log of this side of the equation, because they, after all, are equivalent to each other. And that's going to give me the natural log of K, the rate constant for this reaction, and that's going to equal minus E of A over R. And then I'm just going to split off the temperature down here. Remember, I'm writing it as the equation of a straight line plus the natural log of A, and that is my y-intercept. So this is the y equals mx plus b that I can graph. I can do this. The natural log of K is going to give me a straight line. Here is the natural log of the frequency factor. This is minus E of A over R and 1 over T on the x-axis. Let's say I'm going to run the same reaction at two different temperatures, and I want to know what the relative difference in reaction rates are going to be. I can do that by comparing, let's say, one K value. So we're going to say K, the rate constant 2 over rate constant 1. Now, using my log rules, I can express that as the log of K2 minus the log of K1. And since the log of K is equal to this part of the equation, I can express the log of K2 minus the log of K1, which is, using log rules, the log of K2 over K1. I can express this log of K2 over K1, and I'm simply going to substitute. I'm going to call this temperature 2, and then I'll have another one which will be for temperature 1. And so this is just going to be minus E of A over R 1 over T2 plus the log of A, and that's going to be minus E of A over R 1 over T1 plus the natural log of the frequency factor A. The natural log of frequency factor A is the same for both reactions. We're presuming that E of A, the activation energy, is the same for both reactions. R is the same. The only thing that's going to be different is going to be our temperature, and that's going to give us two different rate constant values, and that's going to give us a different rate of reaction depending on, we're presuming that the higher temperature will be T2. Okay, could be the other way. So since the log of A is the same in both cases, I can go ahead and I can subtract the natural log of A from both sides. Then I'm going to factor out the minus E of A over R. And so now I've got the natural log of K2 over K1 is equal to minus E of A over R times 1 over T2 minus 1 over T1. Now, this is commonly used form of this two-temperature Arrhenius equation. I really sort of have a preference for not liking negative signs, so I am going to simply multiply through and the negative sign, and that's going to give me log of K2 over K1, and when I multiply through, I wind up with a negative 1 over 2 and a positive 1 over 1, and so that's going to be E of A over R 1 over T1, which has been converted to a positive, minus 1 over T2. And that's the derivation of the two-temperature Arrhenius equation. You could use either version of it. Just remember which version you choose to use. This is my preference. Okay, this is the one I prefer, but this one is perfectly valid to use. Okay, the next video will be working a problem using the two-temperature version of the Arrhenius equation.